Tartakovsky, who is visiting us from Stanford University. I like to think of Daniel as essentially a applied mathematician, a computational scientist with a broad set of interests, starting with his early work in hydrology, which has led to dealing with complex media, multi-phase flows, and the difficulty of actually developing ground-up physical models for these systems. Okay, so there you have to make so many assumptions that you may ask whether what you're actually working with as equations has anything to do with reality. And more recently, he's been working on areas of data-driven modeling of physical systems, more recently, meaning for some time now, and asking all sorts of questions about approaches that are sound, meaningful, to deal with these methodologies, asking questions on uncertainty quantifications, parameter estimation, you name it. So this is the context of the talk, which he will be delivering today. You can read the title, it's the role of physics and physics-informed machine learning. I am very much looking forward to the talk and to learn about the methodologies that is being employed on this very interesting, increasingly promising approach to physical models. Thank you very much, Daniel. Please join me in welcoming Daniel Tartakovsky.
So I think this battery seems to be dying.
Okay, I will try to fix it, and then
I could just use this.
Okay. Delivering this.
So thank you all for coming. It's a pleasure to be here. It's my second visit, and usually I would say it's getting only better. This time I was here 5 years ago, so it's not getting better, but it's good. Well, very pleasant to visit at least. So my presentation today is about the work that I've done with Joseph over like the span of, I don't know, 5-7 years. A lot of that. So the work is his. That's why his name is there. But opinions are mine. So do not hold him responsible for the opinions that you might not like in what I have to say next. And so this disclaimer is primarily about the first few slides that I have here. And it's that I added these slides after our conversation in what was that bar? Yes. What I want to mention now for maybe 5 minutes or so is what are the challenges in scientific computing that we think machine learning could solve for us? Like, why is it that everybody is falling over each other to do that? Because there is one issue that is maybe most relevant for sciences than for engineering is whether establishing correlations, which is what statistics machine learning does, is similar to discovering something. So I would argue not, but that's a utilitarian issue. But from the practical point of view, machine learning as a field, it's synonymous with big data, right? So this field thrives on big data, discovers nuggets of gold in a mountain of crap, right? But in scientific computing, in many engineering problems, we are in a data poor environment, not a data-rich environment. So the data that we have are sparse, error-prone, and more importantly, the data do not come from the same populations. So the statistics that you compute is not necessarily representative of the what would happen in the future, what happens in another point in space because of statistical heterogeneity, and so forth. And so then this disclaimers notwithstanding, machine learning and neural networks are clearly everywhere. And why? How are they used? So there are a few bullets here that I think that this, not in, I'm talking about specifically applications to scientific computing, right? Because neural networks clearly have other applications. So in scientific computing, we use them as a post-processor. So if you run your simulations, you generate terabytes of data, you want to understand your data. So that's great to maybe understand what's the low-dimensional manifold on which your data live. Okay, this is not what I'm talking about. This is, I think, is an appropriate use of neural networks. But what about two other ones? So very often nowadays, people use neural networks to solve the differential equation as a PDE solver. And another use is a cheap surrogate of an expensive PDE-based model. So let's dwell a little bit into these two uses. And if we talk about any numerical solver of a differential equation, what do we want from a solver? We want our solver, if you want to publish your new method, say, you want your solver to be ideally two things. You want it to be faster and more accurate, but at least one should be true. For the same accuracy, it should be faster, or maybe for low accuracy, but you could get a fast solution. But neural networks are not necessarily either. So this, what I'm putting here, is a typical relative error with the neural network you used to solve a differential equation. Then these different graphs are for different fitting parameters. It's not particularly important what you are seeing on the x coordinate. What's important is what's on the y coordinate. That's a typical relative error of a numerical solution of a PDE with a neural network. So we are talking about errors on the order of 10 to the minus 2. So that is a not acceptable error for any numerical analyst. And worse than that, it does not converge with the number of samples you throw in. So you are sort of stuck with that error. What I already see, that's again my opinion, not just, so I'm happy to discuss. And another thing is the speed. If you want to solve your differential equation once, almost any numerical method is faster than the neural network. If you take into account training, hyperparameter tuning, the number of days and weeks your students spent throwing out unsuccessful runs, keeping successful runs. So that's a very typical situation. So it's not accurate. And this is if you want to solve a differential equation once. But probably you would not want to do that once, because your differential equations have multiple parameters. So you want to explore the parameter space. You want to do multiple runs of your model. So this is what I would say we call ensemble-based computation. Applications are many. It's in data simulation, uncertainty quantification, design, control, inverse modeling. All those things require hundreds or thousands of forward model runs. So then you would say, okay, then the neural network, so that for the matter, could be faster. And that is true, except that where does the data to train your neural network come from? And more often than not, the data does not come from numeric from observations because we don't have enough observations in physics or many branches of engineering. We have to generate this data on a computer. And how do we generate this data? We solve differential equations multiple times for multiple values of the input parameters. So then the question is, what is faster to solve, so it's your data assimilation or inverse problem, if you need 1,000 runs, or if you need 1,000 runs to train a neural network, there is no point. So there has to be a threshold, right, after with the number of realizations that are needed before neural network becomes a viable surrogate. Okay, so having all of that, having said all of that, I move to applications of machine learning that I feel are profitable and intellectually and beneficial. And actually, I will not, what I will say is equally applicable to many machine learning tools, including neural networks. I will talk about sparse regression. That's what Joe likes to do. But I think this generalizes to neural networks as well. And so what I will talk about two things. One is what do we mean by physics when we say physics-informed machine learning, right? So this is one thing, and I will argue that physics provides us with much more than just the differential equation. That there are things that are encoded in the differential equation that, looking at the residual, minimizing the residual, does not do justice to the physics in those equations. So that's the first part. And the second part is the use of machine learning, artificial intelligence techniques to discover closure relationships. So saying, I'll talk about that. And when we do that, you could use sparse regression, you could do deep learning. I'll talk about the first, but we also use the neural networks for the task. So it will become clear, I think, as I go along. So here's the first part of my talk, or the first part of this second part of my talk, dealing with equation discovery. So we have, suppose we have a classical problem in fluid mechanics, slow number flow past a sphere. We want to compute the drag, the drag coefficient on this sphere. So how would we do it with, so of course, this problem has been solved by Stokes, right, 250 or so years ago. So we know that the drag coefficient is inversely proportional to the Reynolds number, right, with a coefficient of 24, in fact. But if we want to use machine learning, how would we do it? So either we would repeat this experiment 10 times, or we could do this numerical experimentation, right? We could solve Stokes equations n times for different combinations of the density, viscosity, flow velocity u at infinity, different diameters of the sphere. And so this is the set of inputs, right, that control the flow in this case. And these are the experiments for each set of inputs. You would solve numerically, say, Stokes equations, compute the integral over the sphere, you compute the, gives you that coefficient. Okay? And then how does the neural network work? So this is the data. A neural network, pick whatever architecture you want. It has as its inputs, this values S of the input parameters. W's are the weights of the network for a given architecture, right? And then what we want to do is we need to find the weights, so to train a neural network that minimizes the difference between the observations, experimental values, and the neural network predictions. And you repeat it n times, right, over n experiments. And this is where what I was talking about, generating n data points, right, by solving your equation n times to build this, to train this, to generate, to get data for the training of the neural network. And not for, obviously, for a sphere for which we know the result, but this is done routinely in applications of physics and engineering. And nowadays, this is known as discovery of equation-free models, because people will say, this is 19th century to say it's one over Reynolds. We don't get anyway on the computer. We have to put input and output. So having an equation is not a value. We'll just generate whatever network instead of a formula. And what's the drawbacks? The drawbacks, of course, that you need a large number of experiments of the data to train your network. Very likely you would fit the observations very well, because it's have a large number of fitting parameters. But you are just as likely to fail in a generalization task when you are trying to make a prediction and for parameters for which you didn't train your neural network. But more importantly, as you will see in a second, this procedure, no matter how much you try, violates certain physical principles, one of which is symmetry preservation that is encoded in dimensionless numbers. Right, so and this is where is putting physics back into physics-informed machine learning comes in. So what we are saying is that you should not do that, even though you can, or you should not do something just because you can do it. You have to put as much physics, as much knowledge into training as possible. And one of these fundamental pieces of knowledge is the Buckingham pi theorem that tells you how dimensionless groups are related, right? And it's a great tool because it provides an amazing dimensional reduction. So in this case, you start with a 4-dimensional parameter space, and using a pi theorem, this 4-dimensional function would reduce to a single-dimensional function that you need to learn. So this step going from here to here, there are no approximations. It's an exact result. So then now what you're saying we need to learn is a univariate function f. And you could do that with the neural network, which would be an overkill because it's a low-dimensional problem. So we use lasso, which is a regression technique with a sparse regression technique, and this is the so essentially what we are doing here is just as with neural networks. So you are minimizing a difference between observations and your model. It's a linear model, so this n candidates for what could be. In this case, it's say different powers of the Reynolds number, and you want to find the parameters alpha here in this linear regression that minimize this difference to know. But you want to do it in a way that gives you as parsimonious, as simple a model as possible, so that you want to get a good fit between the model and the data, but with as few terms as possible. Right? So you accomplish that by adding this constraint. The weights, the sum of the weights should be as small as possible, so smaller than a certain number, specifying number here. And the trick, of course, here is to, and that's where I suppose you could say that the knowledge of physics come in, is the selection of the candidates for the library. So you could pick sines, cosines, and any function you want. So here we just looked just picked the powers of the Reynolds number, and you cannot see the punchline here because of this. So this is what the model has learned. It's 23.999, no, 3 nines, divided by Reynolds number, whereas the Stokes law is 24 divided by Reynolds. Okay, and all other 39 terms in this series, the model discovered to be 0 or approximately 0. Okay, so that's what the specification does for you. A slightly more complex problem for which some of them there are no exact solutions. So we have, instead of a sphere, we now have an ellipsoid. And if the ellipsoid is aligned with the flow direction in either of its axes, then there is an analytical solution here. And then for the case where the flow direction and the direction of the ellipsoid are misaligned, then in general there are no exact solutions, no results. So that would be something new to truly discover, something that didn't exist before. Instead, there are different correlations and asymptotic results for, like, say, Reynolds number going to 0. So this is then a comparison between the learned model and the exact results. And then for the misaligned flow, this is our slightly more complex formula. So mathematicians, of course, would recall physicists from getting numbers like that. It's clearly fitting, right? These are coefficients that are obtained through fitting and not through physics. That's a tell sign, right? With the physics, you get something like this. But so the error, nevertheless, that doesn't look particularly pretty. The errors are relatively small, right? So the total is, and this is percent error, right? So this is the error of 10 to the minus 3, relative error. And the image over the whole space of the parameters. So phi here is the ratio of the lengths to widths, this A to B in the ellipsoid, and theta is the angle of attack, the angle of misalignment between the flow and the ellipsoid direction. So the errors are small, and you would say that this is great. Right? A successful learning, successful discovery of something that was not known before. So now it's good, but if you are happy to live without a simple equation that you could put on the paper, say you want to do equation-free learning that is given to you by a high-dimensional matrix, that the neural network would provide you. Say, I don't need to do this. I'm just happy to throw all my data into neural network or in a sparse regression in this case, and then see what happens. So if you do that, the method works. It's relatively agnostic to the number of parameters in your model, and you get a comparable error of 10 to the minus 3. In fact, maybe it's even a little better, 10 to the minus 3. Fitting error. But the model that you get, even after specification, has 26 terms. So that's not very parsimonious, you would say, and certainly not very interpretable. But that would still be okay, except for what we see here on this graph that shows a drag coefficient predicted with the machine learning tools, I would say. and as a function of the Reynolds number. And this, what we have here is the following. So the line that you barely see here, it's the blue line, that's a Stokes law for a sphere. That's an exact result, 24 over Reynolds. Our model here, it's 23.999. It overlays the Stokes law that you could barely see, that you cannot separate the two. But what we have here with the rest is the following. So that's where it gets interesting. So we trained our model on data that, like say, flow velocity, the diameter of the sphere, flow density, flow viscosity. So they all combine, even though that, they define Reynolds number, of course, right? So they combine to give a single value of the Reynolds number. So then we pick a different flow velocity, different diameter, different density. They are different, but they give the same Reynolds number. And the same thing in the third experiment, force, whatever. So the symmetry of this pi theorem will tell you that all these experiments should give you exactly the same value of the drag coefficient, because they all result in the same Reynolds number. But that is not the case, what you see here. So some of the models, and they all give you an excellent training area, testing area, everything that you would do as a good machine learner, but they give you nonsensical results. So because there is nothing inherently built into machine learning tools that preserve, say, symmetry in this case. And that, of course, is a fundamental flaw of the methods that don't do that. And of course, you would say, and justifiably say, that only immediate would feed the neural network with data that are not non-dimensionalized, that we have to first non-dimensionalize it, then do our numerical experiments, and then things would be good. But this is just one physical constraint that we are satisfied here. So it's that there are undoubtedly some others that people who study PDEs for living theoretically would understand, so that they are not preserved in these learning techniques. So that's the conclusion then, narrowly, that we should all use dimensionless numbers. I think Issam probably teaches that in many fluids class, but in machine learning, because it's a field driven primarily by computer scientists, they don't care about those things. So we should do that. And yes, but what this points towards is that when we say physics-informed learning, there is a lot that physics informs that is not currently in our training algorithms. So those should be designed and improved in that direction. Okay. Okay. So do I need to leave time for questions too, or can I just consume all hour?
It's advisable
to leave. Yes. Okay. I'll do that. So discovery of differential equations. So there, or here in this problem, I think the question is, what is it that we want to discover if you take a view that there is not really enough experimental data to go around to train a model? And here I would say that the two applications that we found, and there are some others that broadly speaking deal with coarse graining or homogenization, upscaling of of differential equations, either in physical space or in time or in the probability space as here. So the problem is like that. So suppose that we have a partial differential equation with random coefficients. I here that they parameterize our differential operator in space or linear terms. Here, second setting is classical stochastic differential equations, so say Langevin type ODEs. And solutions of these equations are random fields in space and time, random processes. So it's typically how would we solve them? They're Monte Carlo methods, different sampling techniques. Integrating this, these are easier to deal with numerically than stochastic ODEs, but there are numerical ways for each. You will draw realizations of your random parameters or the noise here, and then for each time step you would advance your system. So that's well known. But suppose that what we want to do instead, we want to learn a deterministic equation that governs the probability density function of our random state variables. So that's our task here. And first, before we talk about AI, artificial intelligence, how would the human intelligence approach this problem? People have done that. In the theory of turbulence, in particular statistical theory of turbulence, in other fields since then as well. So what you will do is the following. This is one way, of course, of doing things. So you start with introducing a function, which is a delta function. And the argument here is the difference between your stochastic random process U and the deterministic number capital U. Right? So the capital U is a coordinate in the probability space that spans all possible realizations, outcomes of small u. So then why do we care about this function, the delta function? Because it turns out that if you take the average of this pi, of the delta function, then the average of pi, average of this delta function, is exactly what we want. It's the probability density function of our state variable, whose dynamics is described by those PDEs or ODEs. So in this case, then for this equation, a random equation with random coefficients, this nice property here suggests a two-step procedure. So first, starting with the governing equation, you derive an equation for capital pi, and that's you do it in the sense of distributions. And what happened? I think there is a way to hide it.
What?
I think on the slide.
Or maybe go up then, so we don't need to see the title. Yeah.
It's worse.
Oh.
Sure you want to keep it up?
Oh, I don't know. If you do more, maybe it hides it. Oh, hide.
Do I see it? Hide video panel. Okay, I'm always
You.
to learn something new.
That is a true human intelligence.
You are here, correct?
Yes, thank you. So a two-step procedure, right? So starting with the differential equation, without any sampling, right? Running your model multiple times. First, you derive an equation for pi, and then you average it in the probability space, and you end up with an equation for the probability density function. So that's a standard classical approach that physicists and applied mathematicians pursued. Here's an example for a nonlinear PDE with a random coefficient. So fluids community, you would call it advection of a scalar u in a random velocity field v, and the scalar undergoes some chemical transformations, a reaction term r. So what you would do then, starting with this pi and using some elementary properties of the delta function and differential calculus, so you would map this equation here. And that equation is nonlinear, right, in three-dimensional space, physical space. You map it on a linear equation for capital pi, but now this equation lives in a four-dimensional space, x3, x4, spanned by the spatial coordinates and capital U. And this is an equation that is also has been studied a lot, right? So now this result is exact. So you mapped a nonlinear PDE in the low dimensional space onto a higher dimensional space where you have a linear equation. And as a second step, you would average this equation in the probability space. So Reynolds have done it, many people have done it. So the way it works is before taking the mean of this equation, you decompose the coefficients and the state variable into the mean and the fluctuations, zero mean fluctuations around that mean, and then you take the average, and then without any approximations, or physical approximations, I'm sure there are some mathematical constraints when you can do that, but you end up with the following equation, right? So this equation here has terms that are closed, so the average V is the stochastic average of the input, so you could pre-compute that, but then this equation is not closed because it has this average of the fluctuations, and then this is akin to what's this? Reynolds stress in fluid mechanics. So this term is not known, and that's why there is a need for a closure. And what we are saying is that, okay, so at this point we exhausted human intelligence, but not really, right? Let's get to the next slide, because human intelligence is powerful, and there are different approximations. So there are ways of doing it. So this is for, in turbulence, it's called the large edge diffusivity approximation. In other fields, it's macro dispersion. Kretschmann called the direct interaction approximation. So you could close your equation by computing this coefficients approximately. So you would end up with something that looks like a Fokker-Clarke equation. But these coefficients here are computable in closed form, but yet they are approximate, this model. Okay, and this works remarkably well in many cases for this particular problem. This is the PDF of your state variable. You could see that it's highly non-Gaussian with long tails, and the error is controlled as time evolves, so that's not a simple fit. And you could do that. We have done that in many different problems in many different fields, from fluid mechanics to neuroscience to solid mechanics, whatever. But the line here is that derivation or construction of closures by hand, by brain, is time consuming. Okay, so you will say, okay, not only time consuming, but also labor intensive, and there are fewer and fewer students who want to do that or can do that. So can we replace them with computers, with machines that, or at least ask our students to do that on computers? So let's do the following again, revisit this problem. So we have our differential equation, and we want to discover a probability density function, evolution equation for the probability density function of this U. So what physics information do we have now that we should bring to bear. So one is that we know that the probability has to be conserved. So this equation here has to be written in a conservative form, or should be, or could be written in a conservative form. We also know that in general, when you average things out, so say Maritz 20 formalism would tell you that you would end up with equations that are local in space and time, so integral differential equations. So that's an example is a Boltzmann equation. If you say you want to localize these equations to deal with only with partial differential equations, then we know also that thanks to the power theory, we know that this differential operator here must contain other derivatives up to second order or infinite number of derivatives. Otherwise, you have fluctuations and results are not good. So this is a rigorous fact. And in that case, if you do that, then you end up with equations that have a form of the Fokker-Planck equation, so advection diffusion equation. Another thing that is great, especially for the postmodern world, so that is, we are not trying to find a single truth. There are many closures, just physical closures, computer closures, so any closure that does the job and explainable, generalizes well would work. So it's a good application of machine learning for this. So again, we did that with neural networks, works well. I'll show you sparse regression. The same idea, the same methodology as we used to discover drag coefficient. So we start with the library. The library has all possible terms that could enter your model. So in this case, it's no derivatives, first derivatives, and then second derivatives, including all mixed derivatives. And then the general function then has this form, or a general operator, sorry. Beta are coefficients, variable coefficients that multiply these derivatives. So then, and the goal, as before, this details, then I'll skip. But you need to generate data. So you solve your model n times. And then you post-process that data, you compute distributions using kernel density estimator. And so then once you know that, then you see how close your observed empirical PDF approximates this equation. And you do that by minimizing residual, the discrepancy between observations and the model. You introduce this sparsification coefficient to make sure that you keep as few terms, as few derivatives in this operator as possible. And then again, hyperparameter gamma here is a degree of sparsification. It controls how many terms in your model you end up with. So, okay, so that's in general how the method would work. And the thing that I want to point out is the following. So we looked at two things, right? What's written here is the splitting of the operator into two parts. So you could say, I don't want to rely on any intelligence, but it's going in the wrong direction. How do I? So say you could say that I will use my methodology to learn this whole right-hand side, so the differential operator with derivatives with respect to x. So this direct learning and enhanced learning, you would say that we know that this term we derived exactly. We don't need to approximate it. All we need to approximate is this. So we only learn a portion of the operator. And these are the results. So let's start with the simple model that is the differential operator is deterministic. The only thing that is uncertain is the initial condition. So for this problem, there is the PDF equation is exact. It's written here for any differentiable G. And for a particular case, if G of U is just U squared, so you plug U squared here, so you will see that this exact result should have 1 here, and 2 over here. And so this regression model, sparse regression, recovers this differential operator that we derived analytically, and all the rest of the terms, they are here close to 0, so the sparsifier puts them to 0. That's how we ended up with that. Okay, a slightly more complex problem where our differential operator has a random coefficient. So now you need the closure approximation. So an analytically derived closure that is approximation has this second order derivative. And the model, the sparse regression, recovers this equation well. And then we compare to the errors from 2 strategies. One, just brute force sparse regression, and direct sparse regression, and the other one is where we used some brain and only learned things that we needed to learn. So you could see that this machine learning approach that incorporates everything that we knew about the model. It has better errors, and more importantly, it behaves asymptotically well, whereas sparse regression without any physical input performs well, but the errors are higher. Okay, so we use that also for neuroscience, but I'll skip that. The accuracy, so how do you compute the errors in the predictions of probability density functions? So you different metrics one could use. KL divergence is one of the popular ones that people use in information theory. So we've done that the method is accurate. So I'll just stop here. And again, as in summary, what I guess I'm advocating for is that when we use machine learning in scientific computing or in physics-based physics adjacent simulations, we have to put as much physical insight as possible, just simply taking off the shelf and next generation, next architecture of a neural network does not yield good results, or optimal results at least. Might give good results, but they are suboptimal. So I'll stop here. Thank you.
Yeah, that's much time for questions. Thank you very much then. Okay. Yes, Ranem, اتفضل.
Well, thank you very much for this. So I'm an experimental, so my question is going to be this is useful. Thank you very much for this talk. Maybe you can make a comment on, since you've mentioned the Navier-Stokes equation, on it's a linearized, when it's derived, it's a linearized form when you differentiate, when you derive it. You take a cube and you linearize you cut out the higher order terms. I wonder if you can comment on those higher order terms that have been cut out. What would happen if you try to play with them, or stick them somewhere into your machine learning model?
I think the beauty of machine learning, then it's very easy, and you know where to stick them, these terms. But and it's so the answer to your question is that the more terms you will add to your model, in general, the smaller the error will be on the training data set, right? So that's what in this business is called you would overtrain your model, but that just like in any interpolation extrapolation scheme, the prediction error is likely to increase if you do that. But of course, it is true that very often we have systems with small parameters. Yeah, the small parameters are very important for the dynamics of the system. So this method would throw it out, right? The baby with the bathtub, and would ignore all small terms. So that's a danger.
Thank you for your presentation. I have two questions. The first is a bit of a more technical one. So you said sometimes you use neural networks and sometimes sparse regression. But when you use neural networks, what are the architectures you typically employ and how deep are they?
So we usually use convolution of neural networks. And how deep, I think that there is empirical evidence, right, going beyond. I know that there's some magical number of layers, but then we also looked at encoder-decoder architecture. There are many architectures, but I think it's not really a point of my talk. I would say that you would get similar results qualitatively with any neural network.
Okay, and thank you. And the second question is, in this case, the inputs are usually the parameters for the equations and the outputs are the solutions, correct?
Solutions or quantities of interest.
Yes.
So it's because in the drug force is an integral.
So do you see in the future of physics-informed machine learning a case where the input may be, let's say, images of an experiment itself, where we could bring in computer vision-based models and help them analyze the experiment?
Sure. Yeah, but the problem is you need like this M that I used to sum over experiments. M has to be large.
Yes.
So I'm not an experimentalist, but I work with some. So people would, on a good day, they would give you 10 movies for 10 experiments. So the amount of data is huge, but it's movies, 10 movies, 10 is not really enough to train. So the question is, do you have, are there many applications where you could repeat your experiments, on the order of 1,000 times? But if you could, then of course there is nothing specific. This data could be, and in fact, the beauty of this is that you could combine numerical simulations with movies.
Okay.
Right? Because that's kind of.
Okay. Thank you.
Thank you. Yes. Questions? Okay. We can also take questions from the online audience. Anyone interested, please unmute yourself and ask your question. Okay, Sarah? Just hold on a second, Sarah.
Which slide?
You skipped the slides for the Pitsunagumo equations. I just want to see what went on.
We were just discussing this jokingly. I'm not a neuroscientist. But why does it? I think this one.
Yeah, I mean, you just skipped through it. I wanted us to take a look at what happened with these equations. Yeah.
Okay. So doing you a favor. Thank you. Yes, I appreciate this. I understood it. So what we have here is it's a Fitzhugh-Nagumo model of how neurons, individual neurons fire in the brain. So that's not a neuron in a neural network. It's a neuron in the brain. And so there are many models for this process. So this one is one of the often used one. So there are two state variables here. One is the electric potential of the membrane that's involved in firing, and the other one is a recovery variable that brings it down to the resting state. And so what we have here is a system of two coupled ordinary differential equations, and one of the system is driven by random noise. So this random noise has a certain correlation structure, so it's not white noise. And that's why deriving a Fokker-Planck equation for the joint PDF is not exact in this case because of this presence of temporal correlations. And so this is the model that we learned. And so what we have here, and again, so when you do this sparse regression, you in general, you would have coefficients that are varying in space and time. So if you want to recover the spatially varying coefficients, you have to either do simulated annealing or something else that solves that minimization problem in the function space. So that's hard. So one simple way to do it is to say I want to compute an average coefficient that doesn't vary in space and time. So that's what we are showing here. That if the variance of the noise practically these expansions that we would get, and we know that the localization should happen when the correlation length of the noise goes to 0. And so this in that case this you should have constant equations, and this is indeed what happens when the correlation length is 0.1, but if the correlation length increases, then the model with constant coefficients is not accurate, but the human intelligence models could still recover this, derive the closure variables, closure relations, and then you could get these coefficients that are time varying in this case.
Maybe hesitate a question or two.
Yeah, I'll try.
You hesitate.
Yeah, question.
I'm right.
Okay, so concerning symmetries. Okay, it's always a good thing to actually use model variables that actually encode the symmetries, because in many ways they allow for reduction. We describe the form of reduction, which is in terms of the number of parameters that you need to describe a system, the dimensionless parameters. So you would think that if you run enough simulations, a learning algorithm should be able to recover these structures in a form that minimizes, I don't know, let's say instead of minimizing error, minimizing the number of parameters that I need to describe a given model. Okay, so you would think that learning with sufficiently many experiments should help actually lead us to solutions that reflect this underlying symmetry. Now, why is that not happening? Is it that we're not doing enough experiments? Is it that you need a lot of them? Is it that the minimization procedure needs to be a bit more sophisticated? That's one question. I think another type of symmetry, let's say conserved quantities, okay, which are a result of invariance of our equations under certain transformation groups. Okay, so I'm not going to have a learning algorithm be described in a space which respects these constraints from the start.
I'm going to run the simulations and I'm going to expect it to do reasonably well and recovering model or description that actually reflects the fact that there are conserved quantities in the evolutions that it was fed. Does this happen? I haven't experimented with it, and if it doesn't, why not? Okay, so that's one class of questions. Then there is another class of questions which I, sort of thought of when you showed situations when you impose knowledge about the starting equation and any continuum description of your stochastic equations, or you don't. And then I thought, okay, there is some loss of accuracy that happens. And then I wondered whether we can learn something from the errors. Okay, maybe our procedures are missing something fundamental, and this technique that we are using is actually pointing to something more interesting. Is that something useful to explore?
So two separate questions.
Yeah, there are two separate questions. One has to do with
So one question is I think a fundamental question in statistics, right? Where many results are true for n, for the number of samples going to infinity. And then there is this whole subset of it, what you do when n is small. Right? But I think in this particular case, we tried, right? We looked at this question, and adding the number of experiments did not help. So that's a problem that I think I showed you, that when I mentioned as a numerical method. So you would expect a technique that converges as you refine either your numerical mesh, or as you refine the sampling space or get more samples. It does not happen always, and this didn't happen in this example. And in other problems unrelated to this topic, like where we just wanted to do neural networks for PDE. So I think that the problem is that it's not like this neural networks are not unique. So that there is when you solve a minimization problem, you end up. I'm not sure actually. Maybe people who are more mathematically oriented, whether it's an issue with getting stuck in a local minima, or do you know? It could be that, but the errors are very, very small for all of them. Like the problem is that in the experiment that did well, where things fell on the Stokes law, you get exactly the same error, or the same order error as the one that did horribly. So as an indicator, you cannot even tell whether. So that's an issue as well with predictability of neural networks.
In this case, also because the parameter space is much larger for the dimensional case, then you need much more data. Assuming we have the same data for both the dimensionless and the dimensional case. So I see. So that's an important constraint, actually. Yeah. Yes, you get much better generalization when you do it. Okay, that's a hard constraint.
But it's not a usually high dimensional space. It's right.
Yeah. But it's an interesting hardwire constraint in the minimization. It's somewhat unfair to the machine learning, because you're not giving it all the degrees of freedom that in principle could be available. You're giving it all the degrees of freedom, but you're not constraining it, so the non-dimensionalization constrains it to be in lower dimensions. So,
but I think it's fair. It's just it's clearly easier to learn on a low-dimensional manifold, which is what we've done.
Yeah,
and if you learn, no, but the issue is like I don't think it's a problem with not having enough samples. But maybe.
Totally, drag over a sphere problem where instead of knowing
the experiment in terms of Reynolds number, you did it in terms of the variables themselves. When you chose the variable, when you sample the variables, was this sampling informed by Reynolds number, or whatever Reynolds number comes out to be?
No, because we wanted to look at preservation of invariance, right? So we purposefully picked numbers, combinations of inputs that give the same Reynolds number.
Yeah, we can continue the
Yeah,
discussion.
and the second question was,
It's what we can learn from the errors in the context of closure schemes.
well, that's something that you mentioned the other day. Perhaps you could use it as a testing tool to verify different assumptions that undergird the particular closure, right? So you could see maybe it's wrong in that regime as as time increases. Maybe you should not treat this parameter as a perturbation parameter. So that's true.
Okay, give the audience time to formulate questions. Any questions? All right, if not, please join me in thanking Daniel. So Daniel will be with us tomorrow. Will he be available for visits? If there be interest in that?
Sure, yeah, I think in the afternoon,